you're given an area function, g of w, and it's described as integral from 0 to w of the function 6 plus t to the phi d phi. And you're being asked to find what the derivative of this function would be, this area function. And the fundamental theorem of calculus basically says it's that guy, but with a w.
Oh, I kept trying to put in negative cos.
Oh, you were trying to integrate the sign and kind of work your way through.
Okay.
The fundamental theorem of calculus doesn't need you to do that, because essentially, if you integrate something and then you differentiate it, they essentially cancel each other out. And that's why what you're left with is the original, but just with a w.
Okay.
Anything else?
There was another one with E.
Was it E on its own, which would be question 7?
Let me look again.
Sure.
Oh, it was E from integrated from a negative value to a positive value.
Gotcha.
Number 7.
Right. Now, in this case, my choice is -7. Yours will be different. Now, E is just a number.
Yeah.
So if I asked you to integrate 3, the answer would be 3x. If I said do it from -7 to 7, you would just, do that. Well, integrate the number E, and you get ex. Not e to the power of x, but e times x, right? Ex. And then you can evaluate it at -7 and 7. So you plug in 7, and you get e times 7. Take away, put in -7, you get e times -7. E times 7 is 7e. Take away, e times -7 is -ce. Subtracting something that's negative is equivalent to adding it. And so that would be your answer. If I was doing this one, it would be 3 times 7, take away 3 times -7. So it'd be 21, take away -21. I would end up with 42.
Okay, thank you. That's very clear.
It looks very similar to e to the x, like e to the power of x, but the integral, the antiderivative of e to the power of x is e to the power of x. So quite a different result would happen if that was the guy you were integrating.
Thank you.
You're welcome. See who else we've got. Some people arrived while we were doing that. Let's see if they're all here. Quinn and William, you should be around somewhere. Can you see me? Can you hear me?
Yeah.
Okay, good. We're going to be starting very shortly. The good news is I'm really feeling a lot better. I'm getting very good sleep now. And even although even although I'm probably going to cough a few times today, it's over. So I can tell you now, I will see you on Tuesday. I'm sure this weekend we'll just tidy up any little hiccups I've got. And if I have a little sniffle or whatever when I come back on Tuesday, it's not a major issue. So that's kind of good. Right, we are missing 3 more people. So I'm hoping to maybe wait just a few seconds more and then we'll get started. Okay, let's get started. First thing I'm going to do is finish off 5.3, which basically is the shortcut method for finding the area under a curve, which we will now call integrals. There are 3 new guys in town questions 22, 23, and 24, I think they are. Question 23 wants us to find integrals that look like this one. 1 over 1 plus x squared. In this case, it's 5 over 1 plus x squared. But if you want to find the antiderivative of 1 over 1 plus x squared, the answer is the inverse tan of x. Sometimes I prefer to write it as tan inverse x, like that. If you want to do an antiderivative of 1 over the square root of 1 minus x squared, it's the inverse sine function. And last but not least, if you want to find the integral of e to the power of x, so if I put a number in like, oh, I don't know, 3 to the power of x, its antiderivative isn't just 3 to the x. That's e to the x is a special case of that. It's 3 to the x divided by the natural log of 3. So let's get 22, 23, and 24 out of the way. Here is the guy that we're going to integrate. 5 over 1 plus x squared is 5 times the inverse tan of x. Right? 1 over it gets you an inverse, 5 over it gets you 5 inverse. We're then going to evaluate it at 1 over root 3 and root 3. And so as a calculation, that's going to be 5 times the inverse tan of square root of 3, take away 5 times the inverse tan of 1 over root 3. And that is going to be a major headache to you, because we are going to use the unit circle, as you should in anything to do with sines, cosine, tans, or inverse sines and inverse tans and so on. You're going to use in the unit circle, but you have to do it a little bit more work involved, especially when you're talking about inverse tans. The inverse tan, let's do that as a side issue. The inverse tan of root 3 is in fact the angle, let's call it theta, whose tangent is the square root of 3. So we are going to use this unit circle, and we are going to go hunting for an angle, a theta, right, an angle, whose tangent is root 3. Well, if I look around for angles here and here that are going to give me tangents, and tangents you get by taking the y and dividing them by the x, the two candidates are either pi upon 6, because we always do radians, or pi upon 3. Now, if again, I'll do this at the side. Let's choose pi upon 6. Let's see what we get. If you wanted to find the tangent of pi upon 6, you get the y coordinate divided by the x coordinate, and that ends up being, eventually, after you tidy it up, 1 over root 3, which is not the guy I want. If I then try pi upon 3, then I can get the tangent of pi upon 3, and that is going to be this guy, root 3 upon 2 divided by 1 over 2, which eventually becomes root 3. Bingo! So I want to find inverse tan of root 3. The angle that works for is pi upon 3. So that's 5 lots of pi upon 3. Take away the inverse tan of 1 over root 3 is pi upon 6. So take away 5 times pi upon 6. What's that going to get me? 5/3. Take away 5/6, which eventually gets you 5/6. And there is your answer. So not only do you need to know that the antiderivative of 1 over 1 plus x squared is inverse tan, probably even more awkward, you need to know the exact value of the inverse tan of things like a half, 1, root 3, 1 over root 2, things like that. And you get them from in here. And that's question 22 done. If you move on to question 23, Do that one right now, or at least a version of 23, because we all get different numbers. We're going to do the integral from 0 to 2 of 5 to the power of s ds. So I need to find the inverse tan of 5 to the power of s. So it's basically this guy. So it's 5 to the power of s all over the natural log of 5. That guy there, right, this guy here, is the antiderivative of 5 to the s. We then can evaluate it from 0 to 5 to 2. And that's going to give me 5 squared over log 5. Take away 5 to the power of 0 over log 5. So there's the antiderivative. There's the value at 2. There's the value at 0. Now I should try and make this a little bit prettier. That guy is 25 over log 5. What number is 5 to the power of 0? What number is 5 to the power of 0?
One.
Correct. And so, since these share the same common denominator, you can combine them, and there is your final answer. So a little bit easier to evaluate once you realize that the antiderivative of any number to the power of x is the same number to the power of x divided by the natural log of the base, the number. Excuse me. That's my dog telling me that he needed to go. So he was scratching away there. Now, the last one that we haven't covered is question similar to question 24. It's going to be 1 over the square root of root 2, 1/2, and it's 2 over the square root of 1 minus x squared. Now, all 3 questions that we've done today come from this list here. They are just things you need to memorize. 1 over a square root of 1 minus x squared is the inverse sine of x. So its antiderivative, 2 of them, are 2 inverse sines of x. And then we evaluate them at, in this case, 1/2 and 1 over root 2. So that becomes 2 times the inverse sine 1 over root 2. Take away 2 times the inverse sine of 1/2. And whenever we have sines, cosines, or inverse sines, or inverse cosines, we need to refer to our unit circle again. Now, if I'm, excuse me, I'm essentially interested in an angle whose sine is 1 over root 2. And I know that sines are the y coordinate. So I'm looking for a point here whose y coordinate is 1 over root 2. And if I look at the choices, I've got 1/2, I've got root 2 over 2, and I've root 3 over 2. None of them look like they're that guy. But then look again. Isn't square root of 2 over 2 the same thing as 1 over root 2? Right, so if you multiplied the top and bottom by root 2, you'd get that guy. That tells me that the inverse sine of 1 over root 2 gives me the angle pi upon 4. Now, the inverse sine of 1/2 is much easier. The point that has a y coordinate, because sines are the y coordinate, the point that has a y coordinate 1/2 is this guy. The angle that comes from is pi upon 6. So now I have basically a 1/2 pi, take away a 1/3 pi, 3 take away 2, that leaves me with 1/6 pi. And that is my answer. So we have done 3 special cases. An integral that has a 1 over 1 plus x squared part, which led to inverse tans. A square root one, which is this one, which led to an inverse sine. And 4 to the power of x or 4 to the power of s, whatever letter you want to call the variable, anything that looks like this, and we used its antiderivative to get it. Okay, oh, we got a question or a comment, let me see. Yes, you were right, go into this one. Okay, let's move on then. Our final section for today and for this week. And so that will be part of your homework and online test. And it's 5-4 indefinite integrals, and it's been broken into 2 pieces. So let me just get the thing loaded up for my own benefit. It's actually pretty much what we've already done today and yesterday. So a definite integral would be something like this. A definite integral has numbers to start and finish, so 0 to 1. And the way that we do this is we, well, use the power rule, and then we evaluate it at 0, and we evaluate it at, say, at 1. In this case, you would get 1/4 plus 1, take away a whole load of zeros, and the answer would be 5/4. We call these definite integrals. A definite integral has limits of integration. There are numbers here and here. A definite integral, you always get an answer, which is a number. Even if that number is 0 or negative, it's still a number. So what does an indefinite integral look like? Well, an indefinite integral doesn't have limits of integration. So it would look like that guy. And so when you're asked to do an indefinite integral, you're really being asked to find the antiderivative. Now add 1 to the power and divide by the new power. Add 1 to the power and divide by the new power. But when you do an indefinite integral, you always have a plus c. When you do a definite integral, you always end up with a number as your answer. When you do an indefinite integral, you always end up with a plus c. So an indefinite integral is just another way of asking you to find the antiderivative, which means that a lot of the things and the processes that we used yesterday are just going to get redone again today. The major difference is that we won't have this evaluation stage. All we'll have is a big plus c. So in many ways, it's less work. So just to get the ball rolling, here's a version of one. There's an indefinite integral. Each of these can be done with the power rule. So add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Any constant, any number, just tag an x at the end and finish with a plus c. Now that was really quick. Because we don't have any evaluations to do, right? We don't have numbers to evaluate, you know, an x equals 0 to x equals 2 kind of thing. Our workload is halved, which I think is kind of cool. Now, how about this one? E to the x, 3 sine x, plus 2 to the x. Now, I don't have any algebra to do. Excuse me. Each of these pieces, we can find its antiderivative. The antiderivative of e to the x is e to the x. There we go. If you find the antiderivative of 3 sine x, well, you tell me, what is the antiderivative of 3 sine x? I think someone's typed it in for me. Check it. Correct. -3 cosine x. Now, if you want to do 2 to the x, it belongs to this guy here, right? A just represents the base. This is an example where it's 3. But if you want to do the antiderivative of 2 to the x, you get 2 to the x divided by the natural log of 2. And then, because I do it myself, you must remember to do the plus c. Because if you don't do the plus c bit, Weber's sign will tell you that you're wrong. And Weber's sign is a really weird thing. I don't know why it does this. It must be the way it was programmed. Because to me, it doesn't look right. Weber's sign seems to like to put the C at the beginning. That just looks weird to me. And I'm pretty sure that it'll take this answer. So that's the way you should just get used to it. That's the way everybody does it. But Weber's sign, because it has issues, I guess, sometimes makes things harder than they need to be. Now, this fella doesn't require like multiplications to do, but it does require some algebra. I want to find the integral of this. I can't find integrals of things that look like this. I need to turn them into fractional powers of x. So this guy is a 6th root. That little 6 means 6th root. So it's a fractional power, and it's 1/6. This guy here is a cube root. And a cube root is 1/3. Now, if it had just been the cube root, that would have been correct. But because it's 1 over the cube root, are you all comfortable that it's -1/3 rather than just +1/3, right? 1 over something generates a negative power. Now, these two guys are fractional powers of x, but we can use the power rule on anything that looks like these guys. So I'm going to add 1 to the power. Now, once you add 1 to the power, that's 7/6. You then divide by that new power. Well, dividing by 7/6 is the same thing as multiplying by 6/7. So that's where that came from. Now, in the second one, you add 1 to -1/3, and you get plus 2/3, right? Plus 2/3. And then you divide by the new power. Well, dividing by 2/3 is that guy. And then you finish with add c. So this integral is equal to this guy. And I don't like this, but I can't make Weber's sign not do it. Weber's sign will probably let you write that in and tell you you're correct. But we talked about this yesterday as well. There's a thing that's basically, I call it style points. It's really, there are rules in mathematics about why we do things and how we write them so that we are consistent throughout the world. So the person in France doing this question would write the final answer the same way as I would. And it makes communication between mathematicians, at least, and scientists indirectly, easier because we're all sticking to the same rules. So a little side issue while we're at that. We have came to the conclusion that if you've got 1x, everybody writes x. Agreed? You don't write 1, you don't need it, you call it x. If you've got 2x squared, you need 2x squared. But if you have 2x to the power of 1, don't you just write 2x? We've all agreed on that. We've all agreed on all sorts of rules about what you should and shouldn't write. For instance, if I do a calculation and it ends up looking like this, you don't write 0x. We all have decided that 0x is pointless. If you don't have any x's, don't bother writing 0x down. Now, because we have this consistency in notation, it means that pretty much throughout the world, we all do the same type of math and we all end up writing things the same way. So now let's return to style points. And there are 2 rules for style points. Rule number 1, make the answer look the same as the original. Now, if the original had fractional powers in it, this would be perfectly okay. But the original had square roots, cube roots, sixth roots, whatever it is. So this should be converted into that. So this guy here should be 6/7, and 7/6 is the sixth root of x to the 7. And this guy has got a 3 in the bottom. So a 3 on the bottom means cube root, 2 on the top means x squared. And so that is considered the proper way to write the answer to this integral. And there are two rules. Rule number 1, make it look like the original. And rule number 2 is tidy it up, right? Make it look as pretty as possible. There's really not an awful lot I could do to that, so I'm going to try. So let's just talk about some questions then. I'm going to go to the homework and we'll talk about how we would get the answer to some of these later questions. That way we can cover a wider variety of types of questions. So bear with me. Okay. I'll make this a little bit bigger as well. That might make it easier for those of you working with a small screen. Here we go. Power rule. Nothing's to see here. We've done one like that, power rule and various things. We've just done this one, or at least a version of it. What would you do in question 4? What would be the process that you would do first before you start finding antiderivatives? Okay, someone's typed it in. You're right. You FOIL it out. And then, excuse me, and then you do power rule. Some questions yesterday look like that guy. Can you remember what we would do in question 5 algebraically before we start looking for the antiderivative? So what would I do in question 5 to get it ready for antiderivatives? Have an answer? Move the x from the bottom to the top. Yes. So let me just put a little bit more meat on what you just said there, although it looks like, oh, even better. Josiah told us what it would be equal to. So for the rest of us, let's just show you what our two students said to us. Let's stick the integral there and do the dx, but essentially this guy needs to be rewritten. And you multiply it by x to the -1. Now, if that was x squared, I'd multiply by x to the -2. If that was the square root of x on the bottom, this would be x to the -1/2. And I should have thought ahead. That square root also needs to be written as a fractional power. So that would be the first step. Now, you multiply through, you get this guy. You multiply through, you get this guy. And you multiply, oh, that's a weird one. What do you get if you multiply x to the 1, by x to the -1? What do you get if you do that? Yes, you get 1. And if you kind of want to see how you get that, there are different ways of looking at it. I'm trying to convince you that that is 1. If you want to, couldn't we just call it x times 1 over x? You see that's 1. Another way of looking at it is 1 plus -1, right? Add the powers, x to the 0. Well, x to the 0 gets you 1. You get 1. Now, a little bit of an issue here, and it's with this guy. I can do on this guy here, I can do the power rule and I'll get an answer and it makes sense. For the number 1, I can do the power rule. I cannot do the power rule with x to the -1. So if ever x to the -1 appears as part of a calculation or whatever, it just appears, you have to pause on that and say, okay, no power rule. You have to write it like that. And that did happen yesterday as well. Now you can do the antiderivative, because that's 2 times the natural log of x, add 1 to the power, and then divide by the new power, and that guy plus c. And I know I put the absolute value around the natural log of x here. Sometimes I do, sometimes I don't. Actually, sometimes WebAssign does, and sometimes it doesn't. As long as you don't have a negative value for x, you don't really need the absolute value. Now, style points, that is no good. This bit is good. This bit is good. But that guy needs to look like the original. Right? So always kind of the last thing you should do once you've done everything else and you're looking at what essentially is the final answer, give yourself one more look and say, style points. Aha. Now, if this question here had x to the halves in it, you know, and things like that, then this would be totally acceptable. But it doesn't, right? It has square roots, therefore our answer should also contain those. Okay, let's zoom back now to our homework. Now, question 6 is ready to go. I don't need any algebra. I can find antiderivatives of all the pieces. And that one is a power rule. This middle term is what, 6x? Can someone tell me what this guy at the end will get you? And we did it at the beginning of today. Somebody that's not unlike that guy. What is the antiderivative of 5 over x squared plus 1? Any takers? 5 over x squared plus 1. What is its antiderivative? Ah, we've got someone who wants to have a shot at it. No, I know what you're doing here, Joshua, and it makes sense. But let me show you the antiderivative of that guy to remind you who it is, because you've only just met it today, and so maybe it's not quite in your brain yet. It's that guy. So 5 over 1 plus x squared will get you the inverse 5 times the inverse tan of 1. So the question that used to be there on the screen looked like this guy. So you have to recognize when the thing is good to go, right? We can get its antiderivative. And when we have to do things like we did in the other questions, make it to -1, turn it into a half, whatever it might be. Now, this guy is add 1 to the power, divide by the new power. This guy gets you 6x, and this guy gets you 5 inverse tan of x, add c. And I'm now going to show you, oh, got an answer here. Okay, good, makes sense. So what we're going to do now is return back to that, and I want to show you a little, it's WebAssign's problem, not really ours, but we have to cope with it. In here, you have to put the answer to your question, right? So obviously, it's a matter of just typing in what I wrote down a few moments ago. So here's 2/3, and there's an x. And then the guy next, x cubed, sorry. So x cubed, that was the first piece. That's pretty easy to type in. Then you get 6x. Now, if you try and type in 5 inverse tan, you'd probably go 5, 10, minus 1, x, or something like that. And WebAssign just gets confused. What you want to do then is you want to try and write inverse tan. So if I go over here to the trig, do you see there's a button for it? Inverse tan of x. So you need to find the button for it. Oh, and by the way, I think it's a capital C. You need to find a button for it. If you try and type in tan to the power of minus 1x, sometimes WebAssign just goes, oh, you want me to take a tangent to the power of -1, which is not the same thing as inverse tan. So whenever you have to do inverse sine, inverse cosine, inverse tan, well, you hit the trig button and make sure you hit that one. And that makes WebAssign happy. And when it's happy, we are happy. Now, in question 7, let's find the indefinite integral. I don't need to talk about that one. Would you agree that one is power rule? Good to go, don't need to do any algebra. In fact, since this guy is written as a negative power, can't we just leave the answer as, well, what would it be? Add 1 to the power 4, divide, so you get 2t, oops, in capitals, 2t to power of 4. If you add 1 to that guy, you get -1, right? Add 1 to the power, you get -1. Divided by -1 makes that plus. And so 6t to the power of -1. And then add a c. In this case, that is style points, because isn't the answer the same look as the original? Right, so I don't need to turn that into, I know, 6 over t. And this guy here is just evaluate. Okay, let's see if this one rings some bells. Algebraically, what should I be doing in question 8 before we start doing anything else? What should I be doing first? Looks like we've got an answer to that already. Alex, Joey went said, I believe you can also use arctan, and that will work. You're right, it does. So back to this question. What will we multiply? I'm even kind of telling you what to do here. What will you multiply 3x squared plus 4x plus 1 by to rewrite that in a form that will allow us to get antiderivatives? So in question 8, what would you multiply? Correct. X to -1. And get your general answer and then your specific definite answer. This one, I hope, make my day, guys, make my day. Don't worry about the 0 and 1, because that just means they're mixing and matching now, right? They're doing definite ones as well as indefinite. What is the antiderivative of 9 over 1 plus p squared? What is the antiderivative of 9 over 1 plus p squared? And you are correct. It's 9 inverse tan of p. So 9 inverse tan of the variable, in this case the variable is p. And for some reason I'm in capitals. Now, if the question didn't have limits of integration, right? So if it was an indefinite integral, this would be my answer. Since it has a 0 and a 1 in it, that disappears. And what we do then is we evaluate that guy at 1, like this guy. Take away, we evaluate that guy at 0. Now, the inverse tan of 1 is an angle who gives you the tangent of 1, which you're going to trust me because I know the answer to that. It's pi over 4. And you can't do capitals. It's pi over 4. There we go. And what angle gives you a tan of 0 is just basically 0. And so your answer would be this guy, take away 0, And so your answer would be that. So if you see a limits of integration, we call those definite integrals. And when you're finished, the answer looks like that. Do a version of 10. So I'm going to write this one down. I'll do my own version of it. It is a definite integral, but indefinite and definite are almost the same amount of work. Just indefinite integrals, you have a plus c. Definite integrals, you finish with a number. So we're going to do the integral from 0 to 1. This is a version of question 10. And it's going to be x, 6 times the cube root of x, plus 5 times the fourth root of x, dx. Now, if these two guys were missing, it would be an indefinite integral. I would still find the antiderivative, but just plug a add c at the end. And this one's got a little bit more work, although it's going to be approached pretty much the same way. I'm going to do some algebra on these so that eventually I can get powers of x, and then I can use the power rule. So a cube root is going to be called 6x to the 1/3, and a fourth root is going to be called 5x to the 1/4. So hopefully you're comfortable with a cube root being a 1/3 power and a fourth root being a 1/4 power. What I'm going to do next is multiply these together, and then multiply these two together. So far, so good. Now, at this point, we can use the power rule. If you add 1 to 4/3, you get 7/3. If you divide by 7/3, it's the same as multiplying by 3/7. So that's why you get 18/7. This guy, if you add 1 to it, you get 9/4. And dividing by 9/4 is the same as multiplying by 4/9, which is why you get 20/9. Now, if these zeros and ones were not there, I would just be putting plus c here. But since they are here, I'm going to find a number because it's a definite integral. I'm going to do style points. The original had cube roots and so on in it, so I'm going to turn 7/3 into the cube root of x to the 7. And I'm going to do 9/4 as the fourth root of x to the 9. So there's my style points. Now I'm plugging 1 in, and I'm going to save myself a lot of work. 1 to the 7 is still 1, and the cube root of 1 is 1. So you basically get 1. 1 to the power of 9 is 1. The fourth root of 1 is still 1. Plug 0 in here. 0 to the 7 is 0. The cube root of 0 is the whole thing is 0. And so 0. So I basically got 18/7 plus 20/9. At this point, my calculator is going to take over because we want an exact value. So I'm typing in 18/7. I'm adding 20/9. I'm going to get some horrible decimal, which I did. I'm going to go math, choice number 1, and it's 302.63. And that's your answer. Any questions? I hope you're seeing it's pretty much yesterday's work, right? A lot of it is exactly the same as yesterday, and some of it involves indefinite integrals where you find the antiderivative and finish with a plus c. So for the last few minutes, let's just look at some more homework questions, talk them through. Question 11 is a power rule. I do not care if the powers are decimals or fractions. I will add 1 to the power and divide by the new power and stick a plus C on it. What fractional power will you get out of the 8th root of x to the power of 9? What fractional power will that be? And you're right, x to the 9 eighths. Then you can do a power rule. This one here is good to go, right? Power rule, power rule, power rule. And this one is good to go, e to the x. So I'm pretty comfortable with that piece of the puzzle. And I'm a bit worried about this guy. The best way to look at this fraction is 1/9 of 1 over x. So think of it as 1/9 1 over x, because if you do that, I think its antiderivative is a lot cleaner. Yeah, it would be that guy, of course, plus a c. Right? What I don't want you to do is think that that 1/9 means that this is 9x. Don't do that. It's 1/9 of 1 over x. And if you see it that way, its antiderivatives is a lot cleaner. What would you do for our final question? Mathematically, what would you do to get that into a format that would allow us to find antiderivatives? Any suggestions before we do it? Anybody get any ideas? Okay, show you. You are from time to time going to come across situations which are just novel. You've never seen anything quite like it, but it doesn't mean that it can't be done. It just means that you have to figure out how you deal with it. Well, this guy is squared. So my brain is telling me the first thing I'm going to have to do is to rewrite it in some other format that's going to allow me to find antiderivative. So I'm just going to multiply these two things together. Now, if you multiply the bottom together, you get that. And if you multiply the two top together right now, you get that. Now, these two can be foiled, and you're just going to trust me on this, that you get that. And now we're at this stage. Now, at this stage, it should look familiar, shouldn't it? Do you recognize that this guy, right, and this guy, typical fraction, can be rewritten as a multiplication with a -2 power? And that gets me, that guy gets me, that guy, and this times this gets me 1. And that we can find antiderivative of. This guy we can find. That guy, we have to be careful. Anytime you get a -1 power, you cannot use the power rule. You rewrite it in this format. And that happened today. Right, now I can do the power rule. Add 1 to the power, divide by the new power. The middle guy is a log. And the last guy is an R plus C. And then for style points, this guy here should be written like that. Okay, while you're putting down your last names for attendance, Tuesday, I will see you. I'm confident I will be there. So I finally get to see you in person.